So now that we know how to make a free body diagram, we are going to try and use that to actually solve a force problem. So we're going to, you're just sitting on the edge of your seats, aren't you? We're finally going to solve a force problem. And so let's get on with it. Okay, now we're going to try to connect that free body diagram to an actual acceleration problem. And we're going to look at a little more complex situation here. We have a skier facing down a slope. Common sense tells us she'll slide down the hill, but let's see if we can explain that in terms of our language here of force and direction. Okay, so the first step is to draw a sketch and construct a free body diagram. So here's our sketch. We draw our skier, and none of us can draw this well, or maybe I shouldn't say that. I can't draw this well, so I used one from the book. But we can see here, what do we got? What are our forces here? Well, we have a weight force, which is in the downward direction, but because of the slope of this, we're going to elect to go with a coordinate system in the x and y direction. And you'll see why that makes sense here in a minute. We have a frictional force that is potentially pointing up the hill. And then we have what's called a normal force, and we'll talk about that next time. That is basically holding the skier above the snow. Okay, so the weight force is pulling down. The normal force is basically pushing back up to make sure she doesn't sink in this direction. Okay, so there's our sketch, but we want to turn that into a free body diagram, right? We want to simplify this as much as we can. And so in that case, we only have three forces. We have friction, we have the normal force, and we have the weight force with its components. Now looking at this, if we assume this is small, why is she going to slide down the hill? Well, let's look at what forces are acting in that x direction. We have friction here. If that was the only force acting, she would slide up the hill, right? Because we'd have an external force, net external force in the uphill direction. But it's not, okay? Because weight has a component in the y direction, but it also has a component in the x direction. So that weight component, if we put it up here, is pointing downhill here. And the only thing resisting that force is friction. So if we make friction small, as you would when you have a nice pair of waxed skis, that weight force is going to accelerate you in the x direction, which we've defined here as being down the hill. So that's why we chose that coordinate system, because it gives us a way of thinking about, is she going uphill or downhill? Is that net external force going to be uphill or downhill? Now, what if that frictional force were larger, right? What if she forgot to wax her skis? Well, it's possible that that frictional force would balance that weight force and she wouldn't move at all, right? And what if the slope were steeper? In that case, our weight components might be out here and then out here, which would mean that our downhill component of the weight force would get larger and larger until the hill was at 90 degrees, and then all of the weight force would be down the hill. Okay, so the more steep the slope is, the bigger this force X gets in the downhill direction. So let's solve our problem. We'll have to throw some numbers in here. And let's say the friction amounts to about 45 newtons, which is probably a little high actually for friction for a nice pair of skis. And she has a mass of 60 kilograms. So how quickly will she accelerate down the hill? The governing equation is Newton's second law. We could solve this in the y direction, right? There's a normal force and a weight force. What we'd find there is really that the y component of the weight force would be perfectly balanced with the normal force, okay? Because she's neither flying up into the air nor sinking into the snow. So we know that this force has to be balanced with that force. So we could find this, and then we could find what the normal force was. But we don't need that. Okay, we don't need to know what the normal force is. We really only want that force in the x direction. So we take Newton's second law and put it in x components. And we pay as much attention to signs as we can. We called positive x uphill here. Didn't need to, could have called it downhill. You get the same results. But we called it uphill, so that's positive is uphill. So force friction is positive. And then the force weight in the x direction is negative, is pointing down the hill. Now that's equal to the acceleration in the x direction. Okay, so here you can see basically if this is bigger than this, we're going to accelerate in the x direction. If they're equal to each other, then this will be equal to 0, and since mass can't be 0, acceleration would have to be 0. We rearrange this, so all we're doing is taking this m here and moving it to the other side. And then we can solve this because we know, okay, so there's our equation. Now we need to figure out what our numbers are. We know what our force friction is. So now we just need to determine what this force weight is. To do that, we want to know what this guy is, right? The magnitude of this x direction weight force. So we look at our diagram, or our sketch here. We know one angle here. And so we just think about this as trigonometry, right? We have our adjacent, our opposite, and our hypotenuse. We want the opposite, because it's opposite our angle. And the opposite, to get that, we need to use our sine. Remember, so is sine opposite over hypotenuse. So we sine of 25 times this hypotenuse, that FW. FW itself is mg, okay, gravitation to acceleration times our mass. And so we throw our numbers in here. And you might ask why I don't have negative 9.8, and that's a good question. And the reason is because I've included that negative in the way we set up the problem, right? I knew that force friction was positive and force weight was going to be in the negative direction. So I set it up that way here. And so I've already got the negative sign in our equation. And we find that that force in the negative x direction is 248 newtons. So now we can solve for acceleration. Our sum of forces is up here, divided by mass. And we get negative 3.4 meters per second squared, essentially. Okay, so just to recall what that means in terms of acceleration, after a second, she'll be going 3.54 meters per second. After 2 seconds, she'll be going twice that. After 3 seconds, she would be going 10.2 meters per second, right? And at some point, we'd need to start considering other forces, right? You'd have air resistance that would slow you down as your velocity increased. But at these speeds, that air resistance would be very small. Okay, so that's how we solve a force problem. We need to figure out the net external force, which often means dealing with a 2D type problem. And then we use Newton's law to think about what that acceleration is. Till next time.